was light falling on our detectors. To protect the system, it's got a dust cover on the top of it, so it took a while to calibrate things and before we actually sprung the dust cover. But we did that about a month later. Let me fast forward, and that's what the first light image looked like. So this resolution doesn't do it justice. There are actually 4.5 million stars that fall on these detectors. The cutaways kind of give you a feel for the density of stars, right? This field, as I said, we want to observe a lot of stars, right? And where we have a lot of stars is in the plane of the Milky Way galaxy. So we are observing a field of view that's close to the plane of the Milky Way galaxy. And it can be seen very readily in the summertime. It's in a summer constellation, the constellation of Cygnus. If you go outside about 10 p.m. or so, at the beginning of the night in the summer, and you look straight overhead, you see the summer triangle, 3 very bright stars right overhead, Vega, Deneb, and Altair. And Deneb is the tail of the swan Cygnus. And here it is. Here's Cygnus. Here's the bright star Deneb. We've got the bright star of Vega over here, and then the bright star of Altair comprising the summer triangle. And so here's the wing of the swan, and nestled underneath the wing of the swan, between the bright stars Deneb and Vega, is our field of view. And here you see those modules mosaicked here. It's about the size of my hand, which doesn't seem like very much. It's only 1/400th of the whole entire sky. But by astronomical standards, that's actually a very large field of view. And we have to do special things in our telescope to correct for the types of optical effects that you have when you're trying to image such a large field of view. And just to give you a little bit more perspective, the field is so large that a full moon in the sky, a full moon, would nestle quite cozily in one of these gaps right here. Okay? But the full moon is smaller than you might think. It's only about 1/2 of a pinky finger, okay? So this is a hand, 100 square degrees in the sky. All right, so now I'm going to take one of these CCDs and I'm going to cut it in half and show you one channel just to give you a better feel for the density of stars. That's what it looks like. It's pretty, don't you think? This was our very first light image. We popped open the dust cover, and this was the very first thing that we saw. And I happened to be alone at NASA Ames when it came down. Everybody had gone home because the engineers called us up and said, we're delayed, we're not going to be able to send it to you. And everybody went home, but I had already arranged for somebody to take care of the kids and all this stuff. So I was at Ames all alone, and then all of a sudden we get this email from our engineers saying, oh, we just transferred it to Ames. And there I was, all alone, and I brought it up on the computer, and it just, displaying on the computer, it was like champagne filling a glass. It was really beautiful. You can see not only stars here, every single speck you see is a star, okay? You can also see extended objects. These are all galaxies, and there are many of them. If you let your eye wander over here, you see lots of them, lots of these galaxies. Okay, so now we've launched, now we've started to take data. So what I'm going to do in this talk is I'm going to share with you, first of all, a series of planets that we've discovered, or I'm going to highlight one or two actual planets that we've discovered. And then I'm going to switch, and I'm going to talk about the candidates that we've discovered. And so the distinction I'm making is between a compelling signature in the data that suggests we might have a planet and something that's confirmed. So let me just say that right up at front, okay? But first, the planets. Here's our family portrait. These are my children. They're all very beautiful, aren't they? They look like Skittles down here. Okay. In January of 2010, using about the first 30 days of data, we had our first planet discoveries, and they were these big ones up here, right? We were skimming the cream off of the top. Those are the easiest to detect. These are Jupiter-sized things, even larger. As I said, we could do those from the ground. We don't need really a space telescope to do those, but the data was just pristine. You couldn't even see noise in the data. The signal of that transit was just like beads on a string. It was very beautiful. So we published those, and you can see that with time, we are pushing down to smaller and smaller planets, really honing in on true Earth-sized planets, okay? And so what I'd like to do is actually draw attention to Kepler 10b. This is the smallest planet discovery that we've made, and I'd like to talk to you about it in a little bit more depth. We announced it just this year, just about a month and a half ago. Okay, so Kepler 10 is the star that it orbits. Here we've got our field of view, Cygnus. Kepler 10 is actually one of the brighter stars that we observe. It's a star very much like our own sun. It turns out in mass, radius, temperature, it's very similar to our own sun, but older. It's about 10 billion years old as opposed to 4.5 billion years old, which means that it's not going to be rotating very rapidly, which means it's not going to have a strong magnetic field, which means it's not going to have a lot of sunspots and flares and all of that activity that our own sun seems to show. It's a very quiet